Yes, so I'm very privileged to be here today to talk to you about the amazing things that we've been able to do with Unreal Engine. So I'm Herman Brassard. I'm the product manager for the product. And so I've entitled my presentation, The World's First Visual System to Train Airline Pilots with Unreal Engine. I mean, we know many of us here are in the simulation industry, so Unreal Engine has been used already to do quite a few simulations and have trained some pilots already. The emphasis here is airline pilot to a certain level, so we'll be talking quite a bit about level D qualifications of simulators and what it means when you're connecting that to Unreal. So CAE has selected, as Alban just mentioned, has selected Unreal 5 to do the full flight simulation. We actually started on 4 and then migrated to 5 in the process. And very proud about the end result. So today, my presentation is going to talk a little bit, introduce what CAE is, so what we do as a corporation. We'll talk quite a bit about the full flight simulation. It's such an amazing device, as Alban mentioned, right? So if you get the chance to fly one of those, it's quite fun. So we'll see a little bit how it's built, and we'll quickly focus to the visual aspect of it, so that we understand what we've done with Unreal, and that is essentially one of the innovation vector that we're going to be talking about, and then I'll talk about some additional innovation vectors that we have at CAE. So at CAE, we exist to make the world safer. So essentially, we want to train pilots to make sure that everybody, all of us, are safe when we take a flight. So hopefully that's going to start there. So a quick video on CAE. So you've seen in that video like a few aspects, right? So you've seen some full flight simulators like inside the cockpit. You've seen that we're doing civil and defense type of application as well. So a few numbers about CAE. So we annually train 135,000 pilots in a year, and that adds up to more than 1 million hours in simulators. So we're the world leader. We're located in 70 locations around the world. We not only do airplanes, only simulators, but we actually own aircrafts. So in the full profile of a training of a pilot, we go from different level of simulators all the way to what we'll call the full flight simulator, and we'll be talking quite a bit about that today. But once they've done this, then to get their licensed pilot, they actually need to fly Unreal airplane. Therefore, we actually have the full curriculum that we offer them. So over the years, we've actually delivered 1,300 full flight simulators. So this is the biggest device. You'll see that in some videos. And that does not count the number of smaller level devices that are used for specific trainings, instrument training, and so on, all the way to when they get to the full flight simulator. So CAE also owns, so we've moved from a company that was building full flight simulator to actually operating those full flight simulators. So we have a training center, a number of training centers around the world. We have all the way to 300 full flight simulators that are deployed throughout the world, and we're actually training the pilots for the airline, or we're renting the simulation time for the airline. So you can see the massive footprint that CAE has. So when it comes to actually changing a technology, and we'll be talking about how we introduce Unreal Engine there, so we better make sure that it works well and that it performs, right? So we'll talk quite a bit about the performance. So let's talk a little bit. So this is an image of a full flight simulator, how they look nowadays. They've taken different shape throughout the years. So, but I mean, most of us here are in the simulation business. We understand why simulation is important, right? So the first and most obvious case is cost saving, right? So it's cheaper to actually fly in a simulator to train a pilot than to actually fly the real airplane, to maintain that airplane, to fuel it, and all of those things. So there's an obvious cost saving. There's the obvious safety thing, right? So if the pilot is doing something wrong, if he's flying in the real aircraft, then things can go wrong. In a simulator, you're safe, you can try it again and again. So that leads us to the amount of failures and conditions we're able to reproduce in a simulator, right? So pilots learn when they read their manual and they understand how they go through all the theoretical training course, they actually learn how the aircraft works, but then they have to put it in practice. So when they get into the simulator, so we're able to replicate a number of failures, and failures that are ripple effects across systems, right? So you'll run out of fuel, therefore your electricity is going to go down, the hydraulic, and there's cascades effects that are taking place there that are actually completely simulated because we're simulating every systems. Weather conditions are super important. So most of the training that pilots do in the full flight simulator, interestingly enough, is in low visibility. So it's at night, it's like in bad weather conditions and so on. Yet we spend a lot of time making the image as great as possible, but it's a reality. When they train on bad conditions because the easy stuff is not to be done in a simulator, right? So that's very important for them to develop the right reflexes. So the simulator is actually tested for its accuracy and by the authority. So when we build a simulator, the simulator runs the customer runs a number of tests on it, and then those tests are run by the aviation authorities. We'll talk a little bit more about this, and this is where it gets into the details of how the performance of the simulator is very important. So, interesting fact. The fidelity of the simulation is such that a pilot that has been trained and is operating, let's say, Airbus 320, okay, he wants to change to like a Boeing, for example. So that's what we call a type conversion, right? So he's learned, he's able to do a specific aircraft. He needs to move on to a second one, so to another one. So that full transformation actually and training actually takes place only and solely in a simulator. Meaning that it could be that the first time that the pilot gets into the real aircraft, let's say he's trained, did a type conversion of 787, he would step into the 787 and right away would fly with passengers in the back. So in order to make sure that this is safe, we have that simulation has to be top-notch. So let's dig a little bit on what the simulator looks like. So I won't go through all the components, but I'll just point out a few ones. So at the bottom here, you see the motion system. So the motion system is a set of hydraulic jacks that are moving the simulator, obviously. And those used to be hydraulic. Nowadays, they're electric. I like to explain how the system works. It's really there to simulate the G-forces and not so much a movement of the aircraft, right? So the typical case is, imagine that you're on a takeoff, right? So on a takeoff, we're going to be displaying to the pilot like the scene as if he's moving on a runway, he's moving ahead, right? But we're going to be tilting the simulator backwards so that the G-forces, the gravity is going to sink the pilot into a seat and he's going to feel the acceleration. So we're fooling the senses here where we're telling you, your eye's telling you go straight, but you're actually tilted back. So that's what the motion system is all about. So that, of course, all of the vibrations and the effects that the pilot can actually feel ahead of time, for example, stall conditions. There's a number of elements in training that the pilot has to develop the reflexes and feel those movements in order to predict how the aircraft is going to behave. So very key system. The second one that is more physical in nature is the flight control system. So you see that as this component here. So of course those are all the pedals and the control columns and all those things. So we're capturing, of course, the position of all of those movements, but we're putting force feedback on it as well. Those are all measured with force meters and so on to make sure that it's within tolerance and accurate. But let's move a little bit to the visual system, the interesting part here, because we're going to be talking about Unreal. So look at the construct here, and we'll see that in a video on the next slide. So you have 3 projectors on top, and those projectors are not actually projecting directly to the face of the pilot, of course. So they're projecting to what we call a BP screen. So that's kind of a semi-transparent surface, and that imprints the image into that surface. And what the pilot actually sees, so when the pilot is in the cockpit, he's going to actually look at the visual ball here, and in that ball there's a mirror. So what the pilot looks at, he looks at a mirror that actually projects whatever is on the BP screen on top. So this is a system called collimated display. So this actually allows the pilot to see like the image as being far out with the proper perspective and the 3D effect. So this will lead to some additional constraints of blending and making sure that that image is complete and consistent, and it's going to drive some of the requirements inside of our Unreal implementation. So let's have a look at this. There's video. So you'll see how that's construction. See that's a BP screen. So you'll see the ball coming in. There he goes. You see the reflective surface here. So it's going to go in. So that reflective surface is actually a mylar, and we're using like a suction pump to actually stretch it. And then you see the motion system. In this case, they're testing all the limits to make sure that it doesn't hit any walls and that it actually can come back up. So very impressive device. As you see, it's pretty big, right? So there's room for quite a few people in there, but mostly it's all focused about the pilot and the co-pilot. So let's dig a little bit inside the cockpit, what this looks like. So this is an image of an actual simulator. This is an Airbus 320. We see they have HUDs nowadays on those airplanes. And then you see what we call the IOS, the Instructor Operating System Station. So this is forward-facing, so that allows the instructor to actually control all the malfunctions and assess the position of the aircraft and so on, all the conditions, while actually looking at the crew and understanding what the crew is doing. So the first important aspect is that the cockpit has to be 100% replicated and has to be perfect, right? So there's an area for which everything is measured and the colors have to be right. In most cases, we're actually using the real panels. But interestingly enough, when we do a simulator, we do a simulator of a specific aircraft. And specific aircraft, it's like a serial number, if you will, and in the aviation industry, they call them tail number. So a tail number, you actually see that on aircraft, right? So there's typically an ID, and that's a tail number, that's a serial number of the aircraft. So we're going to be taking the schematics of that specific aircraft and making sure that our simulation replicates one for one that one. The reason is that you may think that all airplanes look the same and are coming out of the factory the same way. The reality is that airlines have actually choices. They can choose the type of engines. They have some selections on the options that goes into the cockpit, the avionic equipment, and so on. So we want to make sure that we're not replicating a vanilla thing, but an actual one. And the airline's going to tell us, this is the aircraft I want you to replicate. This is how we're going to do it. So this all speaks to the fidelity of that simulation and how precise it has to be. So the cockpit panels are either real equipment. So in many cases, we're going to use a real panel that goes in the airplane, and we're going to be connecting our host computer to it, and we're going to be faking simulation conditions to that panel to make it believe that it's actually flying, right? So, and we're going to be intercepting some of those messages between the panels to create some faults and some failures and create the effect we want. So in some cases, it's almost, it's hard to create those conditions because the panel is not designed to do this, but we find ways of creating those effects. So those are for real panels. We can also use simulated panels, and in a sense, this is easier. We just replicate the surface, and every dial and every display is actually completely driven by the software. So, but we have to replicate the same logic in that case. So the visual, you've seen the dome in the previous video, right? So typically it's a setup with 3 projectors, 200 degrees horizontally and 45 degrees vertically on 3 projectors. And as I mentioned earlier, so the refresh rate and the performance of that visual is mandated by the authorities. We'll get into the details in a later slide. So physical setup, so we've seen this one already, right? So this is on the left-hand side. So we're running 3 channels at 4K at 60 hertz. So we have more complex configuration, and this speaks to the ability to actually scale the visual system. So we can go up to 10 channels and more. In this case, it's 10 channels at 4K, but at twice the refresh rate. So this is typically done for helicopter or for fast jet pilots. We have different configuration. In this specific one, it's a more recent design from CAE. So this is you actually open up this visual system, you get into it, the cockpit is inside, and you close it out, and you actually have like a 360-degree system around it. And you notice that in that case, there's no Mylar, there's no mirror type. It's actually the projector is directly like on a BP screen, right? So this whole thing is like a BP screen. So let's talk about the regulations that the authorities put on us when it comes more specifically to the visual system and how it's going to be affecting our implementation. So the FAA is the authority in the US, so Federal Aviation Authorities, and they have defined what is a level D. In Europe, we have the equivalent, and pretty much every country have their aviation authorities that are doing variation of, but it's always a level D, as being the summum or the maximum type of qualification that you can have. So the accuracy and the performance is mandated by the industry, and very important is the absence of negative training. So negative training would be a condition that the pilot would be distracted or would learn from an artifact in the rendering that something is going to be coming up, or trigger on this, which would not be a real condition in real life, right? So all of those things would qualify as negative training. So the pilots are actually, every hour that the pilot spends in a simulator is accredited like a real flight hours. And if you're familiar a little bit with the airline industry and the pilots, everything is measured by the number of hours, right? So if you've done so many hours, therefore you can graduate from a first officer to a captain and so on. So again, this speaks to the fidelity of the simulator. So the pilots have to be trained regularly and assessed regularly to make sure that their knowledge is current on a specific airplane. And interestingly enough, a few years back, the regulations have added additional training. One of those is what's called UPRT, so Upset Prevention Recovery Training. So it's kind of a sequence of events that leads to a very bad situation for the airplane. So essentially is when the airplane would get outside of its flight envelope. So flight envelope is the number of degrees and the speed that the airplane actually flies well. So one of the typical one is if you don't go fast enough, you don't have the aerodynamics, so the plane starts to fall, and that's called a stall condition, right? So that's a classic one. So pilots in those UPRT conditions are trained to recognize the signs, again, with the motion system, with the visual, with the systems that they have in the cockpit before those things happen, so that they take corrective measures to prevent them from happening. But with the simulator, we can put them in those situations, and then they become into the recovery mode where the aircraft has stalled or is outside of the flight conditions. What do you do to recover, right? So you can imagine that there's nowhere else but the simulator that you want to do those things in. So this is to speak to this the fidelity of that simulator. Let's talk a little bit about the visual. So when the visual is assessed for that fidelity, we're looking at the resolution, the field of view, of course. So those are mandated. Contrast, brightness. We even have like light meters that we get in the simulator, and we measure to make sure the amount of light is okay. Very regulated system there. Smearing and motion blur are things that are being assessed. We have test patterns to do this to make sure that it goes well. Anti-aliasing is an important element. I'll talk about it into the next slide, how the standard anti-aliasing that we have in games is not sufficient in some conditions. Refresh rate latency, again, I'll talk a little bit more about those in detail. Light point resolutions. Imagine that pilots, when they land at night. What do you have? You have a runway that has like a number of light systems that are fairly complex. Pilots are trained to actually recognize the runway compared to a highway. Sometimes you'll have a highway with a number of lights that are all lined up and they look just the same as a runway. So those are all important elements that are part of the training. And the absence of bending. So bending is this effect that you can have if you essentially have the same color. Let's say you're in a cloud, right? So and then there's not enough variation in color to have a gradient, and you end up with like one band of one color and the next one being the other color. So this is a no-go, right? So there's techniques in there in our rendering to make sure that we balance this out. So this is on a performance aspect. Of course, the authorities are looking at capabilities. There's a whole slew of feature set that I won't bother you with, but the different weather condition is something they pay a lot of attention to. So it's highly defined in the aviation industry. You have like conditions of visibility, Cat 1, Cat 2, CAV OK, and so on. So where those ranges of visibility are defined. And so they're testing against this. So we'll make sure that if you're at such distance with a certain visibility, you see so many runway lights because they're evenly spaced and all of those conditions. Airport light modelings and control, right? So we have to make sure those are accurate. And the modeling of the airport. So we have every time there's a change in an airport, let's say that they're adding a runway, adding a terminal, taxiways, and so on, we have to keep those models current. So we have 3 months to actually update the visual database and make it current for the training to be okay. Because otherwise, again, it's perceived like negative training. The pilot is going to be training on a runway and expecting certain things. He gets in real life and suddenly it's not the same, right? So we have to keep those things current. So visual performance, so three elements. So you see we're getting closer and closer to Unreal in the visual performance here. So aliasing conditions. So yes, we're using some of the classic anti-aliasing techniques, but in some cases they're not sufficient. You can imagine that one of the cases we have is a pilot approaching, like let's say like a 6 nautical mile approach on a runway, and that runway is fairly far away with a bunch of little lights that are the runway lights, and the motions of the airplane is like very subtle compared to the distance, right? So those pixels are going to, if you have aliasing, those pixels are going to start jumping, and that's going to be very distracting to the pilot. So we have specific techniques on top of the standard anti-aliasing to cover those cases. Popping, so popping is the appearance, sudden appearance of a feature. Let's say, so you're flying, you see villages coming up, so they cannot be popping in the scene, because again, the pilot is doing something and suddenly he sees something that pops, and it's distracting. Therefore, it's bad training and it's bad testing of the ability of the pilot, because he's been distracted, right? So he doesn't have the same reaction time and so on. Frame skip, so essentially an overrun, right? So you essentially you have too much content in the scene, too many animations, whatever you have in there, and then suddenly either the GPU or the CPU overruns its frame. So that creates stutter into the scene, so that's a no-go, right? So we have to make sure that we calibrate and we prevent those conditions from happening, otherwise it becomes negative training. So let's dig into the latency, because that's a big one that offered us a number of challenges when we went to Unreal. And I want to explain to you a little bit some of the context in which we're running here. So one of the tests that is done in the simulator is the latency test. And the authorities give us typically, again, on average, about 100 milliseconds for a complete loop. And what is that complete loop? It's essentially starting a movement on a control column or joystick, an input from the pilot, okay, all the way to the actual image being changed in the scene. And this is actually tested with actuator that pushes the control and a camera that scans the image and computes the amount of time between the two. Okay, so we have to make sure that we're reactive. So let's go into what the control, the loop there, and understand that every of those systems is taking some time. Therefore, the visual system is squeezed into a smaller refresh latency there. So we have about 20 milliseconds that takes care for the flight controls. So flight controls, again, it's the capturing of the input, sending that to the flight model. Flight model is computing all the dynamics based on the weather, the forces, all the conditions, the runway slippery, and all of those things. And then essentially outputs a new viewpoint, right? So this is your new position for the next iteration. So that goes into the visual. So visual has to take that position, and then it enters like 3 different threads. You're familiar with this in Unreal, right? So you have the gaming thread, you have the render thread, and you have the RHI, the render hardware interface thread. So all of those 3 would in a typical Unreal configuration, they would be in cascade, one after the other, leaving each of those essentially the full 16 milliseconds to compute one after the other. But that would be too much. That's too long. So we essentially have to squeeze those into a smaller period of time, which means that you don't have as much time, a complete frame to do all the CPU, then all the GPU, and all the RHI, right? So you're squeezed at doing less in less time, essentially. So, and then it gets to the projector. Interestingly enough, the projector has its own latency, right? So you're sending the image. So between the video scan out and the projector processing, we end up about 25 milliseconds. So we have to consider that, because again, the test is actually looking at the image and not so much just measuring what the system is. Okay, so latency is a big thing that has an impact on our performance and our ability to throw a lot of content into the scene there. So we've talked that there's 3 projectors there, so we of course need to synchronize and to do the blending for this. So the videos have to be in sync, the frame number have to be in sync, right? So every effect, let's say we have snow coming down, right? So every snowflakes have to actually be in sync between all the computers that are rendering those channels to make sure that it's a complete scene. When you do the blending, that's well known in the industry, right? So there's essentially one projector is reducing the intensity as the other projector starts to increase its intensity, such that there's no dual intensity at the crossover of those 2 channels, right? So, and there's a number of calibration systems that are there to making sure that this works. So we have test patterns, and there's a number of calibration doing that. So the overruns, right? So they're not supposed to happen, but if they do happen, you want to limit it to a single frame, right? So the last thing you want is, because there's a little bit too much in a scene on the left-hand side, that the whole scene starts to stop, right? So those are some of our design criteria there. So I've talked about the blending of the display. So this actually imposes a constraint. So anything that is screen space cannot work anymore, because each of the Unreal Engine instances essentially is not aware of the screen space of the other, right? So you have to take those out and operate in a different way. So auto exposures, screen space reflections, all of those things get fooled when you start to put all those screens one beside the other. So simulators takes different shapes. So you've seen the full flight simulator there. So we have lower level devices. So on the second one here is more touchscreen type of display. So those, of course, are less expensive devices, but they serve their purpose in certain training conditions. So pilots are going to learn certain skills there, and at the end they end up into the full flight simulator. Interestingly enough, I forgot to mention, but in a full flight simulator, we even have a smoke generator to simulate that you're in fire. If there's a fire condition, we're actually going to be throwing smoke in the simulator, and the pilots have to be trained to have the reflex to pick up the oxygen mask and start switching their microphone so that they speak through this and then run through their procedures and so on. So it's meant to be quite immersive and develop the right reflexes. So the third one here is our MXR series. So this is mixed reality, and that's running Prodigy as well. So we have one here. This is more of a tabletop type of mission planning for the military. So another way to do visualization, different constraints in terms of how this is being done. And the last one is the dome that you've seen earlier with like the 10 projectors there, where the pilot is completely surrounded. So that's a different way of doing it, rather than having a mixed reality or type of headset. He's actually surrounded by 360-degree images. So let's get into a little bit more on the specific of Unreal now. So CAE has a long tradition of building its own image generator. So it started in 1991, where we actually designed what we call CAE MaxView. At the time, we were like programming DSP, digital signal processors, and FPGAs, and designing our own cards, right? So it was like real hardcore type of development, very specific to what our customers needed. And then in 2003, we started to develop Tropos. So that was, let's take COTS hardware. So at that point, we switched to PC with GPU cards, but we were doing the full software stack. And we ran through a few years of this. You see Tropos 6000, 6000XR. So at doing improvements on the software, to the point that you realize that it's hard to keep up with all the innovations in the video industry, and that's where we made the move to say, let's go Unreal and get an additional level of abstraction, essentially, where our software development is at higher level rather than go down to OpenGL and drive down every rendering element. So that leads us to October 2024, which is pretty much now. And this is, so we're doing the acceptance at the moment of a simulator in Vancouver, and that's going to end up being the Prodigy 1.0 release. You've heard Bill this morning mention that in March, we actually got our first level D qualification in Bangkok. So that was like a performance test to make sure that we're able to reach level D, all the criteria that I mentioned earlier. And now we have essentially like a full-featured product with Prodigy 1.0, at which point we say we have everything that we had before plus, right? So much, much better rendering. And we're getting very good comments from our customers. So what are some of the benefits that we're getting from Unreal Engine, right? So it's, of course, an optimized rendering pipeline. So evolving with all the GPU advancements and so on, global illumination, ray tracing, we can leverage all of those things. The ecosystem of plugins, so we use some of the plugins. We develop quite a bit of our things ourselves as well. We can reuse some content in there. And of course, the talent, right? So the ability to actually it takes somebody that has learned and understands Unreal Engine and ramp them up quickly at developing inside of our image generator is quite interesting compared to back in the days where you had to essentially train them from the ground up, right? So because it was all custom software. So that's significant advantage, as well as all the tooling that enable us to identify all the performance elements. You've seen how focused we are on performance, making sure that things are happening at the right time. So there's great sets of tools that comes with Unreal Engine. So some of the challenges that we had. So round Earth support, because we started earlier, right? So now we have large world coordinates that is getting much better and as a wider coverage in all the feature sets now. We have the seamless content of the paging, right? So we have to be able to fly around the planet. So we have a full Earth model that is there, and we have imagery everywhere. We have to fly and make sure that there's none of that popping coming up and that there's no distractions to the pilot. The anti-aliasing, I've mentioned before, that is taking some specific elements that we have to deal in a specific way. The infamous garbage collector for the performance, so that is each time this thing kicks in, so you're skipping a frame. So, okay, how do we manage it? How do we control it? So, working well with Epic, so improving this, it's getting better and better every time. So, so we're looking at more improvement there, but we found ways of managing it to a certain extent. Latency, as I mentioned, we have to squeeze that into a certain number of frames. And the sensor pipeline. So next in our roadmap, we're going to be starting doing a military simulator where they have like IR, NVG, night vision goggles type of rendering. So in order to do this as physics-based as possible, we need to insert some elements inside of the rendering pipeline in an efficient way, so that we found ways to do this without modifying the engine significantly. So those were part of the challenges. So let's talk a little bit about the content offering that we have. So we have a continuous terrain, a world backdrop. We have an extensive library of airports. As I mentioned before, we need to keep those airports current for the training to be valid. So we have more than 250 airports around the world. Those, we pick the ones that our customer want, the ones that they fly to, the ones that are mostly used. We have procedural airport generation that takes place as well. So for all the ones that have not been modeled, we actually load the avionic data that tells us essentially all the airports on the planet, and we actually draw the runway and put the lighting system, put the terminal, and all of those things based on the nav data. But so our customers are actually using both. They're using the manually created airports as well as the procedurally generated ones. But the authorities does not allow you to train certain procedure on the generic one. They force you to be on the higher fidelity one. So there's, again, regulations play a big role here. And I've mentioned about the airport models that have to be updated. So roadmap, so there's only 2 slides left here. So CA Prodigy 0.1 was the one that we did in Bangkok. So we got our level D certification. We're happy about that. Now in October, we're getting our product ready, full capability, and we're starting to switch gear and get all of the DNS capabilities. So that is lots of sensor, higher speed, more paging, more content. There's a number of requirements there. So we do differentiation between helicopters and fast jet, for example. So helicopters, big effect about the downwash effect, right? So when the helicopter actually goes close to the ground, depending if he's over water or sand, it's going to create different effects. So we need to make sure that this renders well. It's pretty complex in terms of the vectors that the flight model is giving us, the runway, the surface underneath, and getting that recirculation effect to get the pilot to have the right feel of when he's landing in those conditions. And this has to work well with sensors as well. So pilots are going to be landing with night vision goggles. They put the actual real night vision goggles, right? Those little units that renders everything green. Essentially, this is an enhancement of the light. So they're using that when they're landing at night, and all of those effects that we have, like the recirculation, have to be compliant with that. So that is for Prodigy. So let's talk a little bit, just one slide about some of the other innovations that we have at CAE. So I've mentioned that we've gone from designing our cards, our visual cards ourselves, to using more GPU-based and more COTS. So that adoption is not only in visual, it's throughout. So we're reusing components that exist and focusing more on adapting them or on integrating them in order to serve our purpose. So there is an increasing use of VR and mixed reality. So we're working with the authorities there, because in some cases they say for certain training it's okay to use it. In other cases it's not satisfactory. So we're following the authorities. We're working with them to assess which training condition is suitable for VR and mixed reality. And we're coming up with demonstration and feeding onto those analysis there. So Train Where You Fly is another initiative we have. Is essentially, because we have such a large number of simulators throughout the world, is like, why would the pilot actually have to train at the same place all the time? So let's say that the pilot is actually flying to a destination, he has a layover of like two days. Why not pick up the curriculum and say your next session of training is actually in that city that you just landed, and we just so happens to have a period of time that the simulator is available, it's the right simulator configuration, we have the right trainer. Interestingly enough, if you're flying in North America, in the US, for example, you're FAA regulated. The instructor has to be FAA certified. So we end up having to make sure that we have instructors that are certified under different aviation authorities around the world, so that we can maintain that network and have pilots train at the right place with the right accreditations there. So improvement on the efficiency of the training itself. So biometrics, right? So we have techniques to figure out where is the pilot looking at, right? So is he actually circling through all the instruments at the right frequency? What's the reaction time? What's the performance? Comparing the performance of a pilot against the average performance of pilots and so on. So there's a load, there's a big performance analysis and so on. And the last one is like the synthetic instructor coaching. So for more procedural type of things, you don't need to have an instructor beside you to tell you. The computer can do this, can guide you and assess if you've done something, and you can be guided through those various steps of training. So on this, that concludes my presentation on Prodigy and what we've done with Unreal Engine. Okay, so I think that's it. So thank you very much for listening to me, and come and have questions, come to see me.